Why I show these three examples is the purpose is to ensure very early in the design and also in the integration phase, when you integrate MEMS sensors into your product, you want to be very sure that you have not any deficiencies in that device that could harm basically either people or even make your product not really attractive in the market. Okay, when we talk about testing, I need to create a little bit knowledge about what we call system level testing. If you're not in the MEMS sensor, let's say manufacturing business, then you might not know MEMS sensors are these days packed with several dies. So it's not longer a single sensor element, it's really complex systems in these sensors. And as sensors become more and more, let's say, capable in terms of machine learning algorithms, these sensor packages that are still very small contain lots of hardware. So that means when you test such a system, the full operation of the sensor can only be tested when you have a fully packaged part, and that is what we call final test. So we don't do wafer test here, we really test the final system. And what S-test really is a system level test solution. So having said all that, what is S-test all about? S-test is actually existing in two flavors. Spectra offers two flavors of that. One is we call S-test lab, which actually is designed to be used on the lab desk of a developer, or you do some research on early prototypes. And very often this is combined with the exact stimulus setup that you need in the lab. When you have an accelerometer, then you very likely want to have an inertial stimulation system. When you have a pressure sensor, you need to have a pressure chamber, and so on and so forth. But as long as the sensor has a digital interface, you can connect that to our S-test table chassis. And in the end, the setup appears to be relatively simple, and that's the purpose of S-test lab. The purpose is to really have a very compact setup that allows you to be used on the desk, still gives you enough, let's say, flexibility to connect different sensors, but not only one. You want to have redundancy in your lab setups. The idea behind that is really give every developer something on his desk so that he's ready to go. I will say a few words about the integrated components later, but keep in mind we have S-test lab in a small version. So here we can test up to, oh, sorry, mistake here on my side. That is the big one, I'm sorry. So we have actually two flavors of that S-test lab units. The larger one is actually dedicated more for people that have really to verify a larger quantity in the lab, because this requirement exists regularly, that you not only test single sensors, but larger quantities. The units itself remain pretty much identical. The core of that system I will explain in a few slides. So what is the difference in terms of a fab approach? Because the idea that we have with the S-test solution is you give a sensor developer, a software developer, a sensor system integrator, and measurement device that he can easily verify the proper operation of a sensor. But in the end, this system could be also used in final production. And that is a different setup. You see here on the left-hand side the device testing, or the DOT, device under test handling system. So when you are a mass production handling system provider, you provide pick and place solutions for a larger quantity of devices, and you apply all kinds of different stimulus to these larger quantity of sensors, because what you want to achieve is high testing throughput. And for that purpose, you of course need the tester capabilities also for the same parallelity. So here we offer again larger setups that can be easily integrated, and they can easily be scaled depending on your demand of final test. So this is how such an S-test fab rack looks like. We call these units as test 16. And the idea is really they are supposed to be integrated into a larger rack with fans. So these setups are supposed to be standing on the test floor. And of course, depending on the test requirements, these can be scaled to very, very large quantities, depending on how many sensors you need to test at once. So what is the core of that system is, and what is different to maybe to an ATE system, if you might be aware of what an ATE system is doing, testing logic chips like memory or CPUs. The S-test core element we call universal tester board. And what SPEKTRA did is we integrated all resources, all hardware resources that are required to test digital sensors on one board. So we have basically parametric measurement. We can actually supply voltage, we can supply current, we can measure this, and we can basically provide this the energy source for my device under test, and we support 4 different ones per card. The next thing that is essential for the proper test operation is, of course, you have very flexible IOs, which allow us to basically represent any of these digital protocols I mentioned earlier to the devices under test. The card has up to 16 IOs, and we support a data rate up to 20 megahertz. Of course, it usually depends also on the external electrical circuit, what cables you connect to it, how long is the cable, and so on and so forth. You see also the output ranges of that IOs. Then, of course, we have a multiplexer that allows us to measure all these signals back, because this is what the purpose of a test system is. You want to know how much current is drawn by your device under test under certain conditions. Last but not least, we have, of course, an ADC to measure all that. We have also thought a bit ahead to give you the flexibility to add custom circuitry to that board if any of the features that you might need for your test is not covered by the hardware that's already on the card. So for that purpose, we have additional IOs that can be used completely freely by custom hardware. We can measure timings, of course. A lot of the signal integrity and operational tests require a proper timing of signals. We can do that with a resolution of 12.5 nanoseconds. The core of that, I'm sorry, I have to drink. The core of that is, of course, a programmable logic, and that we use to really implement all of these digital sensor protocols. And as we have a full control about the contents of that FPGA, we are not covering all these already. We also can extend these interfaces. Whatever sensor interface protocol might pop up in the future that is not yet visible or not yet important, but some customers ask for it, we can extend that. And that is the big flexibility of such a test system, that we can adapt that to different sensor requirements. What we also provide is, of course, a very easy to use software API to use this tester. There's a simple network TCP layer API to configure interfaces. You see here an example of a tool that we provide where we basically configure an I2C interface. I don't know whether you can see that, it's maybe a little bit too small. But the idea behind that is to give you a really set of simple commands that allow you to configure your sensor. Remember what I said when I showed the different accelerometers in the beginning. Some sensors have measurement ranges, so you have to configure what measurement range you want to use. If you want to measure in a 2G range, you need to configure your sensor. And this can be all done here in this IOS sequence editor. So that's the name of the tool. And we also have 2 different flavors of commands here, real-time commands that allow you to do things very fast, which is essential for high testing throughput. Okay, let me quickly summarize a bit what S-test is all about. It is a cost-optimized solution for testing of digital MEMS sensors. And what we really try to do is create a very low cost per sensor here. Then there are compact setups that can be later easily scaled into fab setups. And the big benefit is ease of use software, and that allows a test developer to transfer his test programs easily from the lab to the fab. And that is we think one of the biggest benefits to accelerate testing.